not just build a machine learning model, but also to put them into production. And so by the end of this first course and by the end of this specialization, I hope you have a good sense of the entire life cycle of the machine learning project, from training a model to put into production, and really how to manage the entire machine learning project. Let's jump in. Let's start with an example. Let's say you're using computer vision to inspect phones coming off a manufacturing line to see if there are defects on them. So this phone shown on the left doesn't have any scratches on it, but if there was a scratch or crack or something, a computer vision algorithm would hopefully be able to find this type of scratch or defect and maybe put a bounding box around it as part of quality control. If you get a data set of scratched phones, you can train a computer vision algorithm, maybe a neural network, to detect these types of defects. But what do you now need to do in order to put this into production deployment? This would be an example of how you could deploy a system like this. You might have an edge device. By edge device, I mean a device that is living inside the factory that is manufacturing these smartphones. And that edge device would have a piece of inspection software whose job it is to take a picture of the phone, see if there's a scratch, and then make a decision on whether this phone is acceptable or not. This is actually commonly done in factories. This is called automated visual defect inspection. What the inspection software does is it will control a camera that will take a picture of the smartphone as it rolls off the manufacturing line, and it then has to make an API call to pass this picture to a prediction server. And the job of the prediction server is to accept these API calls, receive an image, make a decision as to whether or not this phone is effective, and return its prediction. And then the inspection software can make the appropriate control decision, whether to let this phone move on in the manufacturing line or whether to shove it to a side because it was defective and not acceptable. So after you have trained a learning algorithm, maybe trained a neural network to take as input X pictures of phones and map them to Y predictions about whether the phone is defective or not, you still have to take this machine learning model, put it in a prediction server, set up API interfaces, and really write all of the rest of the software in order to deploy this learning algorithm into production. This prediction server is sometimes in the cloud, and sometimes the prediction server is actually at the edge as well. In fact, in manufacturing, we use edge deployments a lot because you can't have your factory go down every time your internet access goes down. But cloud deployments where the prediction server is a server in the cloud is also used for many applications. Let's say you write all the software. What could possibly go wrong? It turns out that just because you've trained a learning algorithm that does well on your test set, which is to be celebrated, it's great when you do well on your whole test set. Unfortunately, reaching that milestone doesn't mean you're done. There can still be quite a lot of work and challenges ahead to get a valuable production deployment running. For example, let's say your training set has images that look like this. There's a good phone on the left, the one in the middle has a big scratch across it, and you've trained your learning algorithm to recognize that phones like this on the left are okay, meaning there are no defects, and maybe draw bounding boxes around scratches or other defects it finds in phones. When you deploy it in the factory, you may find that the real-life production deployment gives you back images like this, much darker ones, because the lighting conditions in the factory have changed for some reason compared to the time when the training set was collected. This problem is sometimes called concept drift or data drift. You'll learn more about these terms later in this week. But this is one example of the many practical problems that we as machine learning engineers should step up to solve if we want to make sure that we don't just do well on the holdout test set, but that our systems actually create value in a practical production deployment environment. I've worked on quite a few projects where my machine learning team and I would successfully nail a proof of concept. And by that I mean we train a model in a Jupyter Notebook and it will work great. And we will celebrate that. You should celebrate it when you have a learning algorithm work well in a Jupyter Notebook or in a development environment. But it turns out that sometimes I've seen many projects where that success, which is a great success, to the practical deployment is still maybe another 6 months of work. And this is just one of many of the practical things that a machine learning team has to watch out for and handle in order to actually deploy these systems. Some machine learning engineers will say it's not a machine learning problem to address these problems. If the data set changes, some machine learning engineers think, well, is that a machine learning problem? My point of view is that our job is to make these things work. And so if the data set has changed, I think of it as my responsibility when I work on a project to step in and do what I can to adjust the data distribution as it is rather than as I wish it is. So this specialization will teach you about a lot of these important practical things for building machine learning systems that work not just in the lab, not just in the Jupyter Notebook, but in a production deployment environment. A second challenge of deploying machine learning models in production is that it takes a lot more than machine learning code. Over the last decade, there's been a lot of attention on machine learning models. So your neural network or other algorithm that learns a function mapping from some input to some output. And there's been amazing progress in machine learning models. But it turns out that if you look at a machine learning system in production, if this little orange rectangle represents the machine learning code, the machine learning model code, then this is all the code you need for the entire machine learning project. I feel like for many machine learning projects, maybe only 5 to 10%, maybe even less of the code is machine learning code. And I think this is one of the reasons why when you have a proof of concept model working, maybe in Jupyter Notebook, it can still be a lot of work to go from that initial proof of concept to the production deployment. So sometimes people refer to the POC or the proof of concept to production gap. And a lot of that gap is sometimes just the sheer amount of work it is to also write all of this code out here beyond the initial machine learning model code. So what is all this other stuff? This is a diagram that I've adapted from a paper by D. Scully and others. Beyond the machine learning code, there are also many components, especially components for managing the data, such as data collection, data verification, feature extraction, and after you are serving it, how to monitor the system. Well, monitor the data comes back, help you analyze it. But there are often many other components that need to be built to enable a working production deployment. So in this course, you learn what are all of these other pieces of software needed for a valuable production deployment. But rather than looking at all of these complex pieces, one of the most useful frameworks I've found for organizing the workflow of a machine learning project is to systematically plan out the life cycle of a machine learning project. Let's go to the next video to dive into what is the full life cycle of a machine learning project. And I hope this framework will be very useful for all of your machine learning projects that you plan to deploy in the future. Let's go to the next video. When I'm Building a machine learning system, I found that thinking through the machine learning project lifecycle is an effective way for me to plan out all the steps that I need to work on. And when you're working on a machine learning system, I think you find too that this framework allows you to plan out all the important things you need to do in order to get the system to work and also to minimize surprises. So let's dive in. These are the major steps of a machine learning project. First is scoping, in which you have to define the project, just decide what to work on. What exactly do you want to apply machine learning to, and what is X and what is Y? After having chosen the project, you then have to collect data or acquire the data you need for your algorithm. This includes defining the data and establishing a baseline, and then also labeling and organizing the data. There's some best practices for this that are not intuitive that you learn more about later in this week. After you have your data, you then have to train the model. During the model phase, you have to select and train the model and also perform error analysis. You might know that machine learning is often a highly iterative task. So during the process of error analysis, you may go back and update the model, or you might also go back to the earlier phase and decide you need to collect more data as well. As part of error analysis, before taking the system to deployments, I'll often also carry out a final check, or maybe a final audit, to make sure that the system's performance is good enough and that it's sufficiently reliable for the application. Sometimes an engineer thinks that when you deploy a system, you're done. I now tell most people when you deploy a system for the first time, you're maybe about halfway to the finish line, because it's often only after you turn on live traffic that you then learn the second half of the important lessons needed in order to get the system to perform well. To carry out the deployment step, you have to deploy it in production, right? The software needed to put into production, and then also monitor the system, track the data that continues to come in, and maintain the system. For example, if the data distribution changes, you may need to update the model. And so after the initial deployment, maintenance will often mean going back to perform more error analysis and maybe retrain the model, or it might mean taking the data you get back now that the system is deployed and is running on live data and feeding that back into your data set to then potentially update your data, retrain the model, and so on until you can put an updated model into deployment. I found this framework useful for a very large variety of machine learning projects, from computer vision to audio data to structured data to many other applications. So feel free to take a screenshot of this image and use it with your friends or by yourself to plan out your machine learning project as well. Thanks also to Landing AI's Dylan Laird and Daniel Biberietta, who were instrumental to developing this diagram. In this video, we quickly went through the machine learning project lifecycle. In order to deepen our understanding of this project lifecycle, it'll be useful to walk through a concrete example. So in the next video, let's step through what these different steps of the machine learning project lifecycle look like in the context of a speech recognition application. Let's go on to the next video. One of the successes of deep learning has been speech recognition. Deep learning has made speech recognition much more accurate than maybe a decade ago, and this is allowing many of us to use speech recognition in our smart speakers, on our smartphones, for voice search, and in other contexts. You may have heard occasionally about the research work that goes into building better speech models, but what else is needed to actually build a valuable production deployment speech recognition system? Let's use the machine learning project lifecycle to step through a speech recognition example so you can understand all the steps needed to actually build and deploy such a system. I've worked on speech recognition systems in a commercial context before, and so the first step of that was scoping. Have to first define the project and just make a decision to work on speech recognition, say for voice search. As part of defining the project, I'd also encourage you to try to estimate or maybe at least guesstimate the key metrics. This will be very problem dependent. Almost every application will have its own unique set of goals and metrics. But in the case of speech recognition, some things I cared about were how accurate is the speech system, what is the latency, how long does the system take to transcribe speech, and what is the throughput, how many queries per second could we handle. And then if possible, you might also try to estimate the resources needed. So how much time, how much compute, how much budget, as well as timeline. How long would it take to carry out this project? I'll have a lot more to say on scoping in week 3 of this course. So we'll come back to this topic and describe this in greater detail as well. The next step is the data stage, where you have to define the data and establish a baseline, and also label and organize the data. What's hard about this? One of the challenges of practical speech recognition systems is the data labeled consistently. Here's an audio clip of a fairly typical recording you might get if you're working on speech recognition for voice search. Let me play this audio clip.
Today's weather.
And the question is, given this audio clip that you just heard,
Today's weather.
would you want to transcribe it like that? Which, if you have transcriptionists label the data, this would be a perfectly reasonable transcription. Or would you want to transcribe it like that, which is also a completely reasonable transcription? Or should the transcriptionist say, well, there's often a lot of noise in audio, maybe there's a sound of a clunk if something fell down, and you don't want to transcribe noise, so maybe it's just noise and you should transcribe it like that. It turns out that any of these 3 ways of transcribing the audio is just fine. I would probably prefer either the first or the second, not the third. But what would hurt your learning algorithm's performance is if 1/3 of the transcriptionists use the first, 1/3 the second, and 1/3 the third way of transcribing, because then your data is inconsistent and confusing for the learning algorithm. Because how is the learning algorithm supposed to guess which one of these conventions a specific transcriptionist happened to use for an audio clip? So spotting and correcting inconsistencies like that, maybe just asking everyone to standardize on this first convention, that can have a significant impact on your learning algorithm's performance. So we'll come back later in this course to dive into some best practices for how to spot inconsistencies and how to adjust them. Other examples of data definition questions. For an audio clip, like today's weather, how much silence do you want before and after each clip? After a speaker has stopped speaking, do you want to include another 100 milliseconds of silence after that, or 300 milliseconds, or 500 milliseconds? It's half a second. Or how do you perform volume normalization? Some speakers speak loudly, some are less loud. And then there's actually a tricky case of if you have a single audio clip with some really loud volume and some really soft volume all within the same audio clip. So how do you perform volume normalization? Questions like all of these are data definition questions. A lot of progress in machine learning, that is, a lot of machine learning research, was driven by researchers working to improve performance on benchmark datasets. In that model, researchers might download a dataset and just work on that fixed dataset. And this mindset has led to tremendous progress in machine learning, so no complaints at all about this mindset. But if you are working on a production system, then you don't have to keep the dataset fixed. I often edit the training set or even edit the test set if that's what's needed in order to improve the data quality to get a production system to work better. So what are practical ways to do this effectively? Not in an ad hoc way, but systematic frameworks for making sure you have high quality data. You learn more about this later in this course and later in the specialization as well. After you've collected your data set, the next step is modeling, in which you have to select and train a model and perform error analysis. The 3 key inputs that go into training a machine learning model are the code, that is the algorithm or the neural network model architecture that you might choose. You also have to pick hyperparameters, and then there's the data. And running the code with your hyperparameters on your data gives you the machine learning model, the accelerated machine learning model for learning from, say, audio clips to text transcripts. I've found that in a lot of research work or academic work, you tend to hold the data fixed and vary the code and maybe vary the hyperparameters in order to try to get good performance. In contrast, I found that for a lot of product teams, if your main goal is to just build and deploy a working, valuable machine learning system, I found that it can be even more effective to hold the code fixed and to instead focus on optimizing the data and maybe the hyperparameters in order to get a high-performing model. A machine learning system includes both code and data, and also hyperparameters, but they're maybe a bit easier to optimize than the code or data. And I found that rather than taking a model-centric view of trying to optimize the code to your fixed data set, for many problems, you can use an open source implementation of something that you download off GitHub and instead just focus on optimizing the data. So during modeling, you have to select and train some model architecture, maybe some neural network architecture. Error analysis can then tell you where your model still falls short. And if you can use that error analysis to tell you how to systematically improve your data, maybe improve the code too, that's okay. But often, if error analysis can tell you how to systematically improve the data, that can be a very efficient way for you to get to a high accuracy model. And part of the trick is you don't want to just feel like you need to collect more data all the time, because we could always use more data. But rather than just trying to collect more and more and more data, which is helpful, but can be expensive, if error analysis can help you be more targeted in exactly what data to collect, that can help you be much more efficient in building an accurate model. Finally, when you have trained a model and when error analysis seems to suggest it's working well enough, you're then ready to go into deployment. Take speech recognition. This is how you might deploy a speech system. You have a mobile phone. This would be an edge device with software running locally on your phone. That software taps into the microphone to record what someone is saying, maybe for voice search. And in a typical implementation of speech recognition, you would use a VAD module. VAD stands for Voice Activity Detection. And it's usually a relatively simple algorithm, maybe a learning algorithm. And the job of the VAD allows the smartphone to select out just the audio that contains, hopefully, someone speaking, so that you can send only that audio clip to your prediction server. And in this case, maybe the prediction server lives in the cloud. This would be a common deployment pattern. The prediction server then returns both the transcript, so you can see what the system thinks you said, and it also returns the search results if you're doing voice search. And the transcript and search results are then displayed in the front-end code running on your mobile phone. So implementing this type of system would be the work needed to deploy a speech model in production. Even after it's running though, you still have to monitor and maintain the system. So here's something that happened to me once. My team had built a speech recognition system, and it was trained mainly on adult voices. We pushed it to production, ran it in production, and we found that over time, more and more young individuals, kind of teenagers, sometimes even younger, seem to be using our speech recognition system. And the voices of very young individuals just sound different. And so my speech system's performance started to degrade. We just were not that good at recognizing speech. as spoken by younger voices. And so we had to go back and find a way, collect more data, other things in order to fix it. So one of the key challenges when it comes to deployment is concept drift or data drift, which is what happens when the data distribution changes, such as there are more and more young voices being fed to the speech recognition system. And knowing how to put in place appropriate monitors to spot such problems, and then also how to fix them in a timely way, is a key skill needed to make sure your production deployment creates the value you hope it will. To recap, in this video, you saw the full life cycle of a machine learning project using speech recognition as the running example. So from scoping to data to modeling to deployment. Next, I want to briefly share with you the major concepts and sequencing you learn about in this course. So come with me to the next video.